We're going to start off with an example and work our way to the actual formulas you need. So, our example, and for right now, just kind of follow along here. Okay, I would not try to write all these problems down. If you want these examples, you can always go back online and copy or print these off later. So, Pete's Jeep Tours offers a popular half-day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. We're going to let our random variable be x, so they just chose x as to be our variable, and it's defined as the number of passengers on a randomly selected day. So what we have here is our probability distribution. So we have values from 2 to 6. The minimum is 2, the max we can hold is 6, so anything in between would be fine. So 2 passengers, 3 passengers, and so on. And then they went ahead and calculated the probabilities of having a certain number of passengers on a randomly selected day. So on any given day, he has a 25% chance of having 3 passengers, or a 20% chance of having 5, and so on. Okay? Now, if I were looking at this probability distribution, and I asked you to determine if it was legitimate, what would you need to check?
The percentages add up to 100%.
So the percentages add up to 100%, and each percentage is in between 0 and 1. Okay? So the easy one, are they all between 0 and 1? Yes, they are. If we added them up, do we get 100%? Yes, we do. So it's a legitimate probability distribution, and that's something you should always check, especially if it's one you're setting up. If you're the one actually creating the probability distribution and you're saying all the values and all the probabilities, you should always check to make sure that you assign the probabilities correctly and you accounted for all of your parts. Okay? Now, what I want you guys to do then is take this probability distribution and with your calculators, calculate the mean. Calculate the expected value of x given this probability distribution. Alright, I'm a little scared right now. I don't like what I'm seeing on a lot of calculators. When we calculate the mean, or the expected value for a random variable, do we need to go into our lists at all? No, we do not use lists. Do I just add the percentages together and divide by the total? No. How do we calculate expected value for a random variable?
Multiply the probability times the x value.
Yes.
For all of them and then add them up.
We take the value of the variable times its probability, plus the next value of the variable times its probability, plus the next value times probability. So in your calculators, I should have seen everybody taking 2 times 0.15 plus 3 times 0.25 plus 4 times 0.35 and so on. Those of you who did that, what did you get for your mean? 3.75. Now, mean and expected value, remember, are identical statements in this case. The mean and the expected value are the same when it comes to random variables. So, the mean is 3.75. What does that 3.75 actually mean? When I say the expected value for x is 3.75, what does that mean? Brandon can't answer anymore. He's already done most of your work. Okay.
On average, the GPA select like 3.75.
All right. On a randomly selected day, so basically on any given day, he should expect to have about 3.75 passengers. Okay? So we can expect to see 3.75 passengers on any given day. Now, the second thing I reported here is standard deviation. I'm not going to make you calculate that on your calculator, but let's go through that process again since we had some issues with mean. If I want to calculate standard deviation for a random variable, what's the first thing I have to calculate? That's with the V, variance. So we start with variance. To calculate variance, you take the value. So 2 minus the mean. So I would take 2 minus 3.75 and square that. And what I get there, I multiply by the probability. So 2 minus 3.75 squared times 0.15 plus 3 minus 3.75 squared divided by 0.25 and so on. So I subtract my value from my mean, get an answer, square it, then multiply by the probability. And then when I do that for every value, I add them all together. Once I get my variance, what do I need to remember to do? Take the square root. So once I have variance calculated, I take the square root, and I get my standard deviation. So the standard deviation in this case is 1.090. So what does that standard deviation mean in context? So our mean said that on any given day we should expect 3.75 passengers.
On average, you'll deviate from that 3.75 by 1.09.
There we go. On any given day, we are going to deviate from this mean by about 1.09 passengers. Okay? So on average, we will deviate from that mean of 3.75 by 1.09. So it's kind of like saying we have 3.75 passengers per day, give or take 1. Okay? So that's kind of what we're dealing with there. So that was just kind of some review from Wednesday, working with discrete random variables, calculating mean, standard deviation. Now, where today's information comes in is if we take this and we transform it somehow. So variable x was the number of passengers he has on a given day. Well, now we're going to start talking money. If he charges $150 per passenger to take the tour, we can define a second random variable, which in this case they define as C, and we call it, or we tell it, or it's going to describe the amount he collects on a randomly selected day. So, notice our new variable C. It has values of 300, 450, 600, 750, and 900. Where are those values coming from?
Passengers on each trip times 150 per.
Yeah, if we're charging $150 per passenger, if he has 2 passengers, that means on that day he's going to collect $300. If he has 3 passengers on a day, he's going to collect $450. So all we did was take X and multiply it by 150. Everyone okay with that? Okay. So notice the probabilities stay the same because in essence we're still talking about having 2 passengers, 3 passengers, and 4 passengers. The probabilities aren't going to change It's just how we're defining our variable now. Okay? So, if I took x and multiplied everything by 150 to get my new variable, what do you suppose I want to do with my mean to get my new mean? So take a minute, calculate the new mean. Do some more practice with expected value. Calculate the new mean of this variable.
Can we just take the open times for the
Okay, what'd you get? Okay, so 562.5. So in context, that would be, what does 562.5 actually mean here? Be in dollars, right? So $562.50. Okay, so the mean amount that he would collect on a given day would be $562.50. Okay, now take that 562.5, divide it by our original mean, 3.75. What do you get? You get 150. So notice we multiplied every value by 150, and what ended up happening to our mean? It got multiplied by 150. What do you think is going to happen to our standard deviation? Multiplied by 150. So take 1.090, multiply it by 150. You get 163.5. Okay. So, new mean, $562.50. New standard deviation, $163.50. So on any given day, he can expect to collect $562.50. But on a given day, he will typically be off from that mean by about $163.50. Okay? So, what this leads us to is our first set of rules. When we take a random variable and we multiply it by some constant, then our measures of position, which in this case, the mean, the expected value, also gets multiplied by that constant. Our measures of spread, which in this case is standard deviation, also gets multiplied by that same constant. So just like when we were talking about random sets of data, if we multiplied every data point by a certain constant, all of our positions, our measures of position, all of our measures of spread change by the same amount. So, in notation, and I do want you to write this notation down because it is important. You will see this notation being used in the homework, on quizzes, on tests. So you need to understand it and know what it's talking about. You also need to be able to use this notation to explain to me what you're actually doing in your problems when you show work. So get these three formulas copied down here real quick, and then we'll discuss what they mean. So when we look at these formulas, what's happening is on the left, we're saying if we take our random variable times a constant, so I take my variable x, I multiply it by some constant a. If I want to find the new expected value, all I need to do is calculate the original expected value. So take the original variable and find its mean. Once I know what that mean is, I can multiply it by the constant, and I'm going to get the same exact value. I don't need to multiply every value and then recalculate expected value using the formula. I can calculate expected value once and then multiply by the constant. So if I want to take 8 times x, all I have to do is e of x times a. So if they give you the mean of one variable, and then they tell you to multiply it, that means the mean of that variable is also going to get multiplied. Same thing with standard deviation. If you take every value times a, okay, you can take the original standard deviation and multiply it by that constant, and it'll get you to the same result. Now, the one that's a little tricky is variance. For our purposes right now, mean and standard deviation are pretty much the only ones we're going to be dealing with. But variance is going to come into play a lot more next week when we come back Monday. Monday, we're going to talk about combining random variables. And when we start combining random variables, we can only work with variances. We cannot work directly with standard deviations in most cases. So you do need to understand how variance changes with these different transformations. So if I multiply my variable by a constant, the variance changes by that constant squared. Why would that make sense? What is variance? Yeah, it's our standard deviation squared. So notice, I have standard deviation. If I wanted to convert this equation to variance, I would need to square both sides. If I take standard deviation squared, it becomes variance. On the right side, it said I could take standard deviation times a, but if I square that expression, the standard deviation becomes variance, but a also needs to be squared to maintain the proper relationship. Okay? So if you're talking variances, when you multiply by a constant, you need to square that constant to multiply it by the original variance. That's extremely important. You definitely want to make sure you know that. Okay? Any questions on this? The gist of it is, if you multiply your variable by a constant, multiply your mean and standard deviation by that same constant. Okay? So let's go back to Pete's tours. So, we talked about random variable C, the amount of money Pete collects on a randomly selected day. Now, in order to operate his business, Pete has specific costs that come into play. So, let's say it costs Pete $100 per trip to buy permits, gas, and a ferry pass. So we're going to let a third random variable, which they call V, describe the profit Pete makes on a randomly selected day. So random variable C was how much money he collected. Random variable V is how much he actually profits on that given day. So 200, 350, 500, 650, 800. Where are those coming from? Yeah, we take out our variable C and we're subtracting 100 from it. If he collects 300, but it costs him $100 to do the tour, that means he's only profiting 200. If he collects 450, but it costs him $100 to run it, he's only collecting or profiting 350, right? So we're subtracting 100 from every single value. That's giving us our new variable. So if we're going to subtract 100 from every single variable, what do we suppose is going to happen to our mean? We should probably subtract 100. So if our original mean was $562.50, what's the mean profit on a given day? Yeah, $462.50. Okay. Now, standard deviation. If we wanted to go through and calculate standard deviation, if I subtracted 100 from every single point, what's going to happen to standard deviation? Why? But why? You're right. So we subtract 100 from the mean, but standard deviation stays exactly the same. Now, why is that?
It's the same difference, it's not a concrete number.
Close. Think about when I multiply my data set, okay? If I take a set of numbers and I multiply them by a number, what happens to the distance between the numbers I create? Like if I was looking at 1, 2, 3, 4, 5, and I multiply those by 5, well, when I multiply, the distance actually gets bigger, right? So I had 1, 2, 3, 4, 5, but when I multiplied, now it becomes 5, 10, 15, 20. Now they're separated by 5s instead of separated by 1s. So the distance between each consecutive number gets bigger. Okay? But if I add a certain value, so if I had 1, 2, 3, 4, 5, and I simply add 5 to everything, that means I'd be at 6, 7, 8, 9, 10. Well, they're still the same distance away from each other. 6 is 1 unit away from 7, just like 1 was 1 unit away from 2. So remember, when we add or subtract, that's like taking the distribution and just picking it up and moving it to a new location. I'm not changing how much it spreads. I'm only changing where it's located. So when we add or subtract, this leads us to our next set of rules. When we add or subtract, the mean changes by the exact same amount as each individual value. So whatever we added or subtracted from the variable, we add or subtract from the mean. But standard deviation stays the same. So get those formulas written down here, and then we'll discuss what they mean. Okay? So what these are saying, if I take my random variable x and I add or subtract a constant, my new mean, my new expected value, is simply the old expected value plus or minus that same constant. If I take my random variable and I add or subtract, my standard deviation is simply the standard deviation it was before. It's not going to affect the spread at all. And so if standard deviation remains unfazed, then variance would remain unchanged as well. So when you add or subtract by a constant, mean will change by that same amount. Standard deviation and variance stay the same. Nothing changes. Okay? So now, if we put this all together, so if we put it all together, this, you don't necessarily have to write these down if you don't want to. It's the same stuff. The last two formulas you wrote down, it's just combining them together. So if we were to multiply and add or subtract in the same problem, so if we were to take one variable and multiply it by something and then add or subtract a constant, then the mean changes exactly as you would expect. You multiply the old mean and then add or subtract the constant. Standard deviation, however, only gets multiplied by the new constant. So the plus or minus on the other constant doesn't change standard deviation. We would only apply the multiplication. And so then for variance, same thing. The addition's not going to change anything about it, but instead of multiplying by the constant alone, we have to take that constant squared. Okay? So when we have a combination of these transformations, mean is going to get changed by everything. Standard deviation is only going to be affected by multiplication. And then therefore variance is only going to be affected by multiplication. Now, we talked about the fact that there are two different types of random variables. There are discrete random variables, there are continuous random variables. Now, the type we used to set these formulas up, Pete's Jeep Tours, was what type? Was that a discrete case or a continuous case? Discrete. How do we know it was discrete?
Because you can list all the variables.
Because we could list all of our different values, right? So, all of these formulas apply to a discrete random variable. We know that because we just showed it through an example. But with continuous random variables, what do you think will happen? We're going to have a whole new set of rules. Good news for you guys is we do not. Discrete and continuous variables react the exact same way under these linear transformations. So if you're given a continuous random variable and they tell you the mean and standard deviation, when you proceed to multiply or divide or add or subtract, your mean and standard deviation for the continuous random variable are going to react in the same way that a discrete random variable would. So all of these formulas apply to both types. Okay? So, we already talked about a discrete case. Let's switch it up and talk continuous. So, one brand of bathtub comes with a dial to set the water temperature. When the baby safe setting is selected and the tub is filled, the temperature, X, of the water follows a normal distribution with a mean of 34 degrees Celsius and a standard deviation of 2 degrees Celsius. So, X is our random variable. That is measuring the temperature in the bathtub. So the distribution is normal. That's important. It's a normal distribution. They tell us the mean is 34 degrees Celsius, standard deviation of 2 degrees Celsius. Okay? Now, in America, do we tend to work with Celsius? No. When we read temperatures, we do it in Fahrenheit. So this 34 degrees Celsius and this 2 degrees Celsius doesn't mean a whole lot to us because we don't work with it a lot, right? So let's define a second random variable, call it y. And variable y is going to take our distribution in Celsius and convert it to a distribution using Fahrenheit, something we do know how to relate to. So recall, Fahrenheit is calculated by taking the Celsius degree times 9/5 plus 32. So basically what we're doing here, to get random variable y, we need to take random variable x times 9/5 and then add 32. So every single value of x needs to be multiplied by 9/5 and then added to 32. Okay? So, if I want to find my mean and standard deviation for y, to calculate the mean, I would do what? I would take 9/5 times, the expected value for x, right? And then add 32. Everything changes the mean, multiplication and addition alike. So if I take 9/5 times 34, and then add 32. Someone do that for me real quick. We get 93.2. So the mean temperature using the baby safe option is 93.2 degrees Fahrenheit. Okay? If I want my standard deviation for y, my transformation is 9/5 times x plus 32. So what's going to affect my standard deviation? The 9/5. So I'm going to take 9/5 times the standard deviation of x. The plus 32 has no bearing on standard deviation, so I exclude it. So all I need to do is take 9/5 times my standard deviation, which was 2, and you should get 3.6 degrees Fahrenheit, right? Okay, so continuous random variable, exact same process as a discrete. So if we multiply and add, we change the mean by that amount. If we multiply and add, we change only by the multiplication. Everyone okay with that? All right, go ahead and end the lunch. Once we know our new mean and standard deviation, so we converted from Celsius to Fahrenheit, now we want to actually talk about probabilities with our continuous random variable. So, Babies R Us says that the temperature of a baby's bath water should be between 90 degrees Fahrenheit and 100 degrees Fahrenheit. Find the probability that the water temperature on a randomly selected day when the baby safe setting is used meets the Babies R Us recommendations. So, we had a normal distribution with a mean of 93.2 degrees Fahrenheit and a standard deviation of 3.6 degrees Fahrenheit. We want to calculate the probability that the bath water is actually between 90 degrees Fahrenheit and 100 degrees Fahrenheit. So we're trying to calculate the probability that our variable y is between 90 and 100. So how are we going to go about that? Using z-scores. Since it's a continuous random variable, the temperature of the water can be anything, right? So it's a continuous random variable, which means we have to use z-scores to calculate our probabilities. So, first thing we would need to do is calculate the z-score for 90. So how would we do that using the numbers in the problem here? How do we calculate a z-score?
90 minus 93.2 divided by 3.6.
Very good. 90 minus 93.2 divided by 3.6. So in your calculators, work that out real quick. 90 minus 93.2 divided by 3.6. What do we get?
Negative 0.88.
Negative 0.88. Okay, so for the z-score for 90 degrees, would be negative 0.88. Then we need the z-score for 100 degrees. So we take 100 minus 93.2, all divided by 3.6. And we get 1.88. Okay, so first step in calculating our probability is take our values and standardize them. Once we have our z-scores, what would we need to do next?
Look at the amounts on the table A.
Yeah, we'd actually look these Z-scores up on table A and find the corresponding probability. So we would look up negative 0.88, write down its probability. Look up 1.88, write down its probability.
When you do that, how do you know how far over to go?
The second decimal place. So you go to the 0.8 on the left column,
Yeah.
and then the second 8 tells you to go up until you're below the 0.08. Okay, so once we find the probability on table A for this, we find the probability on table A for that. What do we do with those two probabilities? Subtract them. So we would take the two probabilities we find, subtract them. Whatever's left is going to be our actual probability that the water is between 90 and 100 degrees Fahrenheit. We okay with that? All right. And that is it.